Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the last video, we finished writing almost everything that we need to render an object. The only part that remains is writing the vertex and pixel shaders. However, we need to fix a couple of problems that keep us from running the test application first. We start this video by fixing these issues and then move on to writing the shaders. Hopefully at the end we'll be rewarded for our hard work with a nice rendered image of our 3D model. The first issue that we need to solve is that the render function now expects valid information about the scene. We need to provide an instance of frame info that contains a list of high-level render item IDs, a list of LOD thresholds, and the camera ID. Although we have a camera that we could use for all 4 of the test windows, it's better to dedicate one camera to each render surface. This is because windows with different sizes can have different aspect ratios, and if you would use the same camera for all of them, then we would need to set the aspect ratio and consequentially recalculate the projection matrix for every frame. So let's combine our camera struct with the render surface struct to create a camera surface, for lack of a better name. Then instead of having 4 render surfaces, we'll have 4 camera surfaces. I'm not concerned too much about the structure of this code, because this is the test program and as long as we don't do stuff that smell like dirty hacks, then I'm mostly okay with it. The create and destroy render surface functions will become create and destroy camera surface. And we need to update a bunch of references to the members of our new struct. As I mentioned, when a window is resized, we need to set the aspect ratio of the camera that belongs to that window. In create camera surface, we create a game entity and a camera in addition to the render surface. We also set the aspect ratio as soon as the camera is created. In destroy camera surface, we first remove the surface and the window, followed by the camera and its game entity. We don't have to create a camera in the initialization function. Finally, we can pass the camera ID of the camera for each surface that's being rendered. I'll fix the parameter type in the forward declaration of destroy camera surface and we can give it a try. It failed because the camera ID is invalid. And I don't know why. Stepping through the code, I can see that everything is going as I'd expect, but somehow the ID becomes invalid? Can you see what's happening? The camera ID in the frame info is invalid, but when I look at the camera instances, they do have valid IDs. So what's going on? It must be a small typo I made somewhere. Going through hundreds of lines of code right now, and I don't see anything that looks suspicious. So what is it then? Oh, I forgot to fill in the render item count, so it was taking the camera ID as the number of render items, and the real camera ID was still invalid. Okay, let's try again. Our two-world array seems to be out of range. That's because I forgot to expand the arrays when we create transform components. And that's easily fixed as well. Now we can finally run the program. Although we don't see anything because we still have to write the vertex and pixel shaders for our geometry. First, we need to define the format of the vertex elements that's used by the geometry. Looking at the elements types, which we defined in this video, we can see that we need to define an HLSL type for each of these elements types. For our current 3D model, I know that it uses this element type for all of its submeshes. So for now, I'll only define the static mesh type with normals and textures. We'll see how to deal with geometry that uses different elements types in the next episode. The format that we are defining now has an unsigned integer which contains the tangent space signs. It also contains color information, but that's optional. The next fields are the packed normal and tangent vectors, which we need to unpack in the vertex shader. The last field contains the UV coordinates of the vertex. For future reference, I add a comment here that tells us the enumeration number of this element's type. We start with getting the vertex position by directly indexing into the vertex buffer. We use the vertex index, which is basically a value coming in from the index buffer that we set in the render function. Note that this is a rather different way of pulling in vertices than the more traditional way, where we had to define and set an input layout and get the vertices through shader parameters. We multiply the vertex position by the model to world matrix of the game entity in order to transform each vertex to world space. Next, we need to get the vertex normal vectors from elements buffer and unpack them. For now, we are only interested in normal vectors and will ignore tangents and UV coordinates. We read vertex elements in the same way we read the positions. We can reconstruct the normal vector using the x and y components and the sign of the z component, which we can infer from the second bit in the sign's integer. Please watch this video if you'd like to know how vertex elements are packed. The x and y components of the normal are packed as 16-bit unsigned integers using this function. In order to unpack them, we need to do this in reverse, which is the same as the unpack function here. We can define a constant which we use for unpacking. Simply multiplying the packed normal components and subtracting 1 will get us the unpacked x and y components, from which we can calculate the z component. Because the Z component can be either negative or positive, we must multiply it by the sine of the normal. Now we have everything we need to fill in the output of the vertex shader. In order to get the homogeneous position, we multiply the position by the worldview projection matrix. We already have the world position, and to calculate the normal in world space, we transform it by the inverse transpose of the model to world matrix. Note that by changing the order of multiplication, we effectively use the transpose of the inverse world matrix. We can leave the tangent and UV coordinates untouched, since we are not using them for now. Shader compilation failed because I made a typo. Can you spot it? Because it took me a minute to find it. Shader compilation failed again, and unfortunately this time we get an error message that doesn't tell me what the problem is. Let me check the compiler options to see if we enabled the 16-bit types. Those are pretty new and are not enabled by default. This looks okay to me. Let me run the program and check the error messages again, maybe I missed something. I don't see anything useful here. Let me have a look at the shader then. Okay, found it. I was using the same register for both vertex position and element buffers. I wish the shader compiler would give a more useful error message in this case. Okay, now we can run the application, but I don't see anything. Maybe the camera is looking in the wrong direction. Let's make this more explicit. If the game entity that we are creating is a camera, it will be rotated towards the negative z-axis, looking into the scene. We also set the camera at a distance from the origin so that it's not inside the geometry that we are trying to render. And I just thought of a mistake that I make every time I make a renderer. I almost always clear the depth buffer using a wrong value, and I see I made the same mistake here again. At least as long as we are not using a reverse depth buffer, we should clear it to 1 and not to 0. Fix the parameter when we call create one game entity. Still nothing. Now I really have no idea what could possibly be the matter. Let's try this. Nope. Okay, let me get rid of this code in GPass module that we were using to draw fractals and don't need anymore. Maybe there's something in here interfering with the rendering. So we don't need this anymore. We also don't need the root signature and PSO, because we create those per material now. This looks fine, but this function is no longer needed. And these can go as well. Let me check if we get sensible values for the index count. That looks plausible as well, but I still don't see anything. Camera's direction and position are all set correctly as well. Remain calm, it's not that hundreds of people are watching or anything. Let me tilt the camera down a bit, maybe it's not looking directly at our object. Still nothing. Oh, by the way, we do have entity IDs now that we can pass to the render items. Nothing to do with our problem, but needed fixing anyway. I really need to stop making copy-paste typos like this. Sometimes I wish I could get in a time machine so I could go back in time and slap myself. Unfortunately, I don't have a bat suit. Okay, so I was accidentally using the position buffer for element buffer and per object data, and by doing so I was transforming our geometry to Alpha Centauri. Setting these correctly should solve the problem. Fingers crossed. Look at this tiny guy here. Why is it so tiny? I'm glad we got our first render and all, but I'd hoped that it would be a bit more impressive. Oh well, let's have a look at the 3D model and check if it's scaled correctly. I thought I'd exported it using the correct scale, but it's shorter than 10 centimeters. Okay, let's make it bigger then. I want him to be about 185 or 190 meters. This looks about right. Now that we are here, I'd also like to make this model a bit asymmetrical, so that we can check if we are rendering it correctly. That it's not mirrored or flipped, for example. To do that, I'll just make a little extension on his right shoulder. Well, it would take more time to make it aesthetically pleasing, but that's not the point of this. I'll set the edge hardness for these edges, and then we can try this model instead. First, we need to import the model using the level editor. Here we can see that it has these little thingies on his right shoulder. And in order to save it to a file that we can load in the test application, I need to uncomment this line. Now when I open this model in the editor, it will also be saved to the model file that's loaded by the test renderer. And there it is, our first render that doesn't look totally wrong. Here we can see that although the render target is resized correctly, the aspect ratio doesn't look right. So that's something that we'd like to fix in the next episode. It does look a bit like the silhouette of a ninja, doesn't it? Obviously we are not calculating the color because we don't have lights and textures, but we'll start with that part soon. For now we can use the normal vectors to color each pixel. By doing this, we can see right away that there are all kinds of things that don't look right. For one thing, the shoulder extension appears to be on the left shoulder, and while the model appears to be facing away from us, I can see the round eyepiece, which looks rather confusing. So yeah, there are definitely some things that we need to fix, and we'll do that all in the next episode. I appreciate this video was a bit chaotic, and I hope that you enjoyed watching it nevertheless, and are as excited as I am for the next videos, where we fix all these issues and continue with lighting our scene. Thank you so much for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!